That's about all we can say about this planet. We can tell you the mass and the radius and the density and how far away the star is. And beyond that, we have to turn to models to say anything about the planet. This data is rather limited. However, with this, if you make a discovery that NASA is involved with, you do get a nice animation. So I'm going to tell you about this animation made by my friend and colleague Dana Barry. We're imagining that we are on a spacecraft visiting the planet in a star. You can see here the planet. Look how small it would be if we were far away looking at it compared to the star. But as we get closer, the planet will get bigger in our view. Now, the planet is so close to the star, we're believing that its atmosphere is completely gone. There's no atmosphere on the planet at all. Furthermore, it's tidally locked. It shows the same face of the star at all times, just like the moon does to Earth. This is a favorable energy source. It's got a dark side and a bright side. And here the artist is showing flecks of dust like a comet tail that's coming actually from stellar wind eroding the surface of the planet. Now we're going to zoom in on the planet and look at the hot spots. So this planet has a permanent day side and a permanent night side because of its orientation. And this lava, actually, it's not from volcanoes. We believe that this planet is so hot because it's so close to the star. The surface is hot enough not just to melt lead, but also to melt rock. The surface would look like this. The planet has no atmosphere, so the sky is right up there. It would be a fun place to visit. As long as you have your astronaut spacesuit. So people do make complicated models about these planets, three-dimensional, with convection, trying to understand how the planet cools. And we can watch the movie one more time. So we can leave the light off and we'll watch the movie one more time. Okay, it's just going to zoom out now, so I'll go back and watch the movie. Let's watch it one more time. We'll just let you watch it without commentary. I will give a bit of commentary. So we're zooming in on it. I wanted to explain that tidally locked thing again. It has a permanent day side and a permanent night side. And basically every time it orbits the star, it also rotates one time. It's just like the moon, it shows the same face to Earth at all times. And we believe that this is just because of tides on the planet and the star that make the planet evolve to that state. So in this case, there is a lot of artist license here, but it was certainly fun to work with the artist. Something I got to do and help figure out what this planet might be like. This planet is heated. Expected daytime temperature of more than 2,500 degrees Fahrenheit. Hotter than the lava flows here on Earth. Question is, will its internal energy have completely dissipated? Likely not. Because of radioactive decay, it has a constant but somewhat low level of energy. But its gravitation, energy from gravitational accretion, would certainly be lost. But exactly how cold the night side is definitely a contentious question. Because people don't understand. I'm just giving some technical details for the astronomers. They don't really understand what happens at high pressures in the interior of these planets and how material really behaves, and is it liquid or solid? Does solid say convection dominate or conduction? These are all things that are ongoing issues that are being studied. Two planets is correct. Okay, now I'm going to tell you a few other Kepler things. Because I'm trying to convey to you, I call phase 2 of discovery. We're discovering so many things, and before, we found these big planets close to the star. We called them hot Jupiters. We got used to those. And then people found Jupiters even closer to the star. And those then were called, instead of hot Jupiters, very hot Jupiters. And so people got used to those. And then new graduate students just consider those normal. Okay, so you think that after the first 15 years, we're used to, or we've found everything that's crazy, and used to things. But I'm trying to convey to you that no, things are still changing. New discoveries are still happening that are still surprising exoplanet scientists. Here's one that came out recently, Kepler. It's called Kepler 11. That was the system found after Kepler 10. And look here, there are 6 planets orbiting this star. This is just an artist's conception, because again, we don't spatially resolve anything like this, so only point sources in a distance. And this system is fascinating. 5 of the planets have orbits that would be closer to their star than Mercury is to our sun. And we learn about solar system planets here in school. You know, you learn, oh, Mercury's so close to the sun. It's so close, yet this system has 5 planets that are even closer. And when people look at stars that are young with disks of gas and dust, there's not enough material that close to the star to form planets. And so it's really pretty amazing. And the Kepler team was just fascinated by this. There's 2 really interesting things about the system. One is, what kind of planets are they? They're so close to the star, maybe they're like Mercury, big rocks. But actually, these planets are not big rocks. You know what they are? They're actually, we call them mini Neptunes. They're about 2 Earth radii. And they must have a substantial amount of hydrogen gas. And this is really interesting because it's not clear. They must have formed really far from the star where they could get all this gas. And all kind of moved in perhaps in lockstep, migrated in close to the star. So what these planets are doing there is really, really not known. And these actually have, I'm getting kind of excited about just these technical details, but the rest of my talk is not as technical, so just bear with me for a minute. The other thing that was interesting is these planets are gravitationally interacting. They're very close to each other, such that a single planet transiting its star, it's repeatable to many decimal places. Its period would be known to like 3.5, 1, 2, 4, 6, 8, 9, like that. But these ones aren't. They're not precisely repeating. They're actually not precisely repeating at all. A planet in a system that has about a 30-day period, actually, you know what, its period would vary by about 10 minutes because they're gravitationally interacting. And those interactions and those perturbations can be measured to get the mass of the planet. And so that's why the system is so interesting as well. Now, I have a lot of stuff. I do have a lot of interesting technical things. I think I do have to skip them over, but we can come back to them in the question period. They're a little more complicated. Pardon me?
Are any of those tidally locked?
I think that's a good question. I mean, we have, one of the things about tidal lock is, you know, we have no observational way to measure if the planet is tidally locked. So if we measure it, do we expect them to be tidally locked? I mean, dynamically, it's a great question. I don't know the answer to that. I'd say from the time scale, yes, but the fact that they're all interacting with each other might actually have changed that time scale. Okay, so we'll come back to this. But guess what? Kepler didn't just find this one multiple planet system. It has found a lot of multiple planet systems. And this figure here is made by my colleague, Dan Faberke. It's showing you period in days. So here's 1,000 days, 100, times 1. And this, you can again think of as distance from the star. Period and distance are interchangeable by Kepler's third law. And this here is just, there's no axis here, it's just number. So what he's showing you is Kepler object of interest, it's a number. And this corresponds to the size of the planet. So for example, up here, this one would have 2 planets. This one has 1, 2, 3, 4, 5. This one has 2 big ones. And Kepler has found many multiple systems. And to see more than one transiting planet, they have to be very coplanar. More coplanar than our own solar system. And Kepler didn't just find these. Look how many it found. And this is just in the first several months. So Kepler has shown us that there are multiple planet systems. Many of these can have masses constrained by transit timing. And there's going to be a lot of exciting work to do. But I did want to tell you one more thing about Kepler. And this again is another series of figures showing you period in days, again, distance from the star. And this is size relative to Earth. So before Kepler, we had a bunch of transiting planets. Most of them are big. They're Jupiter size. So you can see it here. But then when Kepler made its first data release, it changed the picture like this. And more recently, in February, look how many planets Kepler found. But the subtlety here is that these are not confirmed planets. They're just planet candidates. Because remember the graph that showed the planet, the starlight dropping in brightness as a function of time? Other things in astrophysics can mimic that signal. And to go from a planet candidate to a planet takes a huge amount of work. It's something I can tell you a bit more about in the Q&A if you're interested. But the way I look at it is like this. If we took all of the telescopes on the ground that could do follow-up, that could take a planet candidate and turn it into a planet, we took all of the astronomers, not only here, but everywhere in the world, and asked if they would all devote their life to confirming the planet, Kepler planet candidates to planets, we still couldn't do it. It's not just a time thing, it's also a limitation, a technology limitation. But that Kepler 10b I showed you, I call that a 1,000 people hour project. Basically took 1,000 people hours to get that one from a planet candidate to a planet, and that was an easy one. So we're not going to know which of these are planets. Kepler never promised to say that star is a planet like Earth. Kepler promised to deliver statistics, the frequency of Earths. And for that, you don't need to know exactly which one is a planet candidate and which one is a planet. You only need to know approximately what rate the planets are really planets, what's your false positive rate. And so that's what Kepler is doing. And Kepler is just simply changing exoplanet science as we know it. Now, before I leave here, this figure, I just want you to look at the data and see if you can tell which kind of planets are most common. Where's the density of these points the highest? See, where are the most planets? I hear people whispering. Does someone want to just shout it out? Interaction part lecture. Between Earth and Neptune. Now, there is a bit of selection effect because Kepler hasn't found as many as it can down here yet. Between Earth and Neptune. And this is amazing, really, because people don't understand this. Why are there so many Neptune-sized or smaller planets? People believe that you either get planets like Earth that are terrestrial, or the standard theory of planet formation, that planet masses grow to about 10 Earth masses, and then they're massive enough to basically accrete, to grab all of the gas all around them and runaway growth into a giant planet. And in fact, the way that Uranus and Neptune formed in our own solar system is not understood. People have a contrived scenario that, oh, they took so long to form, the gas in the disk was just running out, and they just gathered whatever was left. But in fact, now we have to go back to the drawing board because it turns out that these Neptune-sized and smaller objects, they're not only common, they're way more common than others. And so this is the way that Kepler is changing exoplanet science. We don't understand why there are so many Neptunes. And to summarize this part of my talk, discovery of new kind of exoplanets and exoplanetary systems, like those tightly packed ones, like the fact that exo-Neptunes are extremely common, is ongoing with continuous new surprises. So the field continues to deliver new discoveries. And it's really going to keep unfolding as Kepler continues to find new planets. And exoplanet science is changing from studying individual objects to statistics. So we have 1,200 planet candidates, and we will look for patterns in the data and try to explain them. Do you have a question? Yeah, go ahead.
Most of these around single star or double or binary?
Oh, good question. Are most of these around single star or double stars? They're all around single stars. And in exoplanets, you can say, what's the next cool thing to be found? And I think the next cool thing is going to be a planet around a double star. And planets have been found around a star where there's another star that's bound, but it's so far away, it hardly counts. And so they are looking for planets that are so-called circumbinary, because people see disks of gas and dust that are two stars in the middle, and that disk surrounds both of them together. And so they should be there, haven't found them yet. The Kepler team is looking. And because Kepler has 150,000 stars, there's enough there, so if anyone's going to find it, Kepler will. So it's an ongoing issue.
Most stars are born in binary, so they don't understand the exact relationship between the stars.
Most stars are born as binaries, and so what's the question?
It's the question that the diffraction sort out in terms of the frequency of lines all around single stars. So that basically counteract the binary diffraction.
But it's a really good question. The question is, most stars are born as binary. How come I say they're all around single stars? That's a really great question. I'm going to have to think about that. I mean, it's probably true. Kepler is probably just avoiding all those binaries. And unless they're eclipsing binaries, let me think. No, it's really, actually, that's a very deep question. I'm going to have to give that some thought, and we'll have to talk about that later.